thank you. First of all, thank you so much for having me. Thanks, Alexander. Thanks, Zinji. I was talking to Eleonora. London might be my favorite place in the world, but I've never given a talk here. Wow. So I'm super happy. And I know that I missed the party, but I went to the theater, so it's fine. And it's really a pleasure. And thanks, actually, Eleonora, to make this happen too. So let me start by apologizing, like the good Catholic boy that I once was, because this will be actually a lot of metaphysics and a little foundational work. This is just because I honestly, when I was preparing this, I was thinking mostly about me rather than you. And I am writing a book, and I have a contract with Oxford University Press in which, on theories of location, especially philosophical logic and metaphysics, and these will be in the chapter on the applications to philosophy of science, so we cannot actually, we need to have something that goes, let's say, in 20 pages, which I cannot actually have 10 pages introducing affine spaces, or Hilbert spaces, so on and so forth. And so I'm writing this with Fabrice Correia, which is one of the leading metaphysicians and logicians of today's. So, and I promised him to actually get some feedback. So I have a new notebook for the feedback. Okay, good. But, so it's about location, but I wanted to put something, and I know Brian probably was coming, so I put something, a slide that says QFT. Just in case. But the first, oh wait, it's not. Maybe I should do this.
You have to click on the screen.
Go back to the, sorry.
Maybe, yeah.
That's
So let me say that location is important in physics. So my mom, when I was thinking, I got a contract from Oxford University Press, and my mom literally said, they're paying you to write a book on location, on where things are. To which, of course, you replied, they're not paying me, right? So, they're literally not paying me. So, but location is important. I tend to think it is important. In fact, in physics too, this is a beautiful old paper by the 60s by Whiteman, in which it has this new localization scheme that, if you look at it, is being used by all the theorems that you guys know about localization of particles in QFT. If you look at the so-called localization schemes, it comes from this paper. So it is important in philosophy of physics. So here's a beautiful paper by Thomas Pushby, in which he compares location relations and persistence between philosophy of physics and metaphysics. And of course, this is Brian's slide, let's say, because I don't know you guys, but maybe you are into QFT. So consider the following thing. So I don't know anything about this, beside that Brian does these things. So I don't know literally anything. So but consider celebrated results against an ontology of localizable particles in QFT. Let's say Malamud is the famous one, then Egerfeld had couple, and Clifton and Albertson actually had the generalization of it for unsharp properties. You will always find this. The thought here is that you have a map, like from subregions, let's say, of a given Hilbert plane to projection operators in the Hilbert space. And then you will have this thing which corresponds roughly to the following proposition. The system is located within that region here. And this localizability condition basically tells you that there is no way to detect a particle in one subregion of space and then in another region, which is disjoint from it, which they belong to the same Hilbert plane. Now, why am I putting that? Because this seems, on the face of it, just a ban on multilocation, a phenomenon that is very well studied in metaphysics. And in particular, I can tell you that now there's a lot of sophistication of axioms in the literature on formal theories of location that bans multilocation, and they're not actually equivalent. So here's a couple, which we will not go into that, but I can show you that this just says that the location relation is a function rather than just a relation. This is actually turns out to be stronger than this one, as a matter of fact. So I can show you that for an extensional methodology, for if you give me just basic set theory, this entails this, but this doesn't entail that. This is literally logically stronger. This is just to say that there are different, very sophisticated ways to actually ban multilocation. And it will be interesting to see how they match to localization conditions. And I'm saying that because I cannot do this work. Because this is too much. I mean, honestly, I don't know anything about QFT, and the math goes beyond my head. So it's just to say, to ingratiate the project to you, because I'm not doing that at all. So this is the last time you will see. I mean, I know the conditions, but that's basically it. So we're going to do something way, way, way more basic. So, this is the plan for today instead. Now, usually the talks I give them, they have very, very, very simple structure because otherwise I myself get lost. So I will dive right into it. But if you lose, the general dialectic, just tell me. I don't mind actually being interrupted. So, and I'll tell you where we are, okay? And we start by something to which I know even less about, which is quantum gravity. Like I literally don't know almost anything, but I was working with someone that did. So, and the thought is that you might have read that in several approaches to quantum gravity, space-time is emergent. Meaning at the fundamental level, you have nothing like a spatial-temporal structure. You don't have space-time, you don't have metric spaces, you don't have anything like this. But you want to have it at the emergent level because, according to some people, so for example, Chris Woodrick is the one that Vanessa and Robert and Brian and I know because he was in Geneva, right? The emergence of space-time actually undermines the threat of empirical incoherence. Empirical incoherence means roughly the view that the truth of a theory undermines actually the rational, the belief in you believing that it's true. Okay. So the thought is that, well, even if you don't have it fundamentally, but if you have it at emergent level, you're going to be fine. All the reasons that you had to believe your quantum gravity theory, be it string theory, loop quantum gravity, spin forms, whatever, to be true, you can still have it. So it's important. Now the thought is that no one literally basically knows how to understand emergence in this particular case. At least that's what I've been told. But there's an infamous argument that tells you how not to understand it. Whatever you think, the argument has it that you cannot understand it merologically. It cannot be just you cannot give a purely merological account of space-time emergence. Meaning, you cannot do what sometimes in metaphysics we have done for a long time, like sum things up, and then some of these actually sums, merological sums, will cross-categorically actually fuse into something else. So you might be, Russell actually had it for a long time, right? He thought that objects at a certain point, he followed Hume in thinking that objects actually are just fusions of properties. Okay. And the thought is that in the case of space-time, you cannot have this simple view. Why? Because there's this argument from intimacy that tells you, in this particular case, it will not work. Now, why am I interested in that? Because it seems the argument exploits an intimate relation between location and parthood, which is what the book is about. That's why I got interested. Not because I was interested in quantum gravity programs. I honestly don't know anything about them. The intimate relation is that wholes inherit their locations from their parts. Why is Eleonora here? Well, because all her parts are here. Something like this. And inheritance of location, it is thought, fails when spatial-temporal entities emerge from something non-spatial temporal. Okay. So we're going to dig into this argument pretty deep. So we will see that, so at least this is what I think and what Fabrice and I think. There's a natural way to resist the argument. And the argument appeals, so the way that we're resisting appeals to something technical about the locations of regions of space-time. Okay. However, unfortunately, we will see that there's a related issue in some construals of just pure classical quantum mechanics, non-relativistic, that cannot be solved that way. And this is in a very controversial particular way of understanding quantum mechanics, which is mostly due to David Albert and Alice Sané. Okay. And this cannot be solved that way. So my hope is that I'm going to try to discuss a general strategy that works in both the quantum cases. So you have a more general one. So that's the plan, basically. Oh, by the way, for those of you who are interested, but I'm not sure that there are any, because theories of location is a very small field, like we are 10 in the world, so I'm not sure that you know about literature in formal theories of location, in the logic of location. There is a small discussion about the location of regions itself. And there the orthodoxy seems that you have two choices, and they're just a matter of convention. Nothing deep, hinges on that. You can just choose whatever you want. Here's Achille saying that. Here's Josh saying that. Already like almost 10 years ago now, saying, look, you can think that regions of space-time are located at themselves, or you can say that they're not located anywhere. It really doesn't matter. It's just a stipulation. Who cares? I'm going to show you that it matters. In fact, the argument that I'm going to exploit actually tells you something about this. There's way too many people there. I'm scared about this. Okay, good. So this is for those of you who are interested in the theories of location, which Someone might be or might get interested after today. Please talk to me about this if you are. So, okay, so let me go through to the argument. So the argument of intimacy exploits the supposedly intimate relation between parthood and location. In particular, it comes from Ted Sider, which literally writes it like this. If X is part of Y, Y is located wherever X is located and vice versa. Now I'm calling it up, so he doesn't call it upward inheritance. I'm going to call it upward to distinguish from other inheritance principles that I think they're different, they're inequivalent, and it's unclear whether they stand or fall together. Okay. As of now, it's just very, very vague. So, and here is the argument. So I put the lengthy quote just to say that I'm not cheating. Now, in fact, it started from me writing actually to Sam. This is Sam Byron, that he works in quantum gravity. That's why I started. I mean, not the quantum gravity thing. I thought, hey Sam, why don't you just do that? And then we started chatting, okay? So this is what he taught. Well, so you'll have it in the references. So this is just to say I'm not really cheating. I'm not making a problem up. I'm not solving a problem that no one actually raised. Because that's very Italian, so I just wanted to, So, but here's the argument, let's say. So the thought here is that there is a view which is that the easiest way to understand actually emergence of space-time is just via meteorology. It's just a sum of spin foam or a sum of strings or whatever. It's just a meteorological sum. In fact, this is much weaker. Every meteorological account will entail this, but this will not entail, for example, the composition talk, if you know a little bit about meteorology. So this is the weakest version you can have, and the thought is that any space-time region has known spatiotemporal parts. Now, if you think about a point in space-time, then we'll have only known spatiotemporal parts besides himself, of course. Okay? And of course, if you think that parthood is a partial order, then every region will have points as parts. In fact, sorry, because I wanted to, so let me get this thing. And by transitivity, every region will have known spatiotemporal parts. Now, I'm going to assume that, in fact, I'm going to assume that space-time regions are just a model of classical meteorology, which if you don't know what it is, it's just basically that just things set theoretic structure. It's just purely set theoretic structure. So the thought is that there's a powerful intuition here that regions are somewhere, for any region, R is located somewhere in space-time. And then thought upward inheritance, a little bit more precisely, but not precisely enough. For any space-time region R with known spatiotemporal parts, R is located wherever x1, xn are located. And so the thought is that once you have this, you can reconstruct it as a classic argument for the inconsistency of these 3. So one has to go. That's why I'm doing this. It's just a classic, paradigmatic example of a classic philosophical argument. You have 3 that seems independently plausible, but they're just inconsistent together. So here's the argument. Let's say, given space-time meteorological emergence, I have the space-time region, think about the point, between spatiotemporal parts. By upward inheritance of location, it's located wherever these parts are located, but those parts are not located, so R is not located. But by regions are somewhere, all spatiotemporal regions are located. Contradiction, they're both located and not located. Now, the first reaction, if you are a logician or a metaphysician, a nitpicking one, as a matter of fact, like we are if we do formal theories, you might think that you might be able to resolve it just referring to a very precise principle of location. Because you might think, look, there's clearly different ways, right? So there's a way in which I am where my hand is, right? But it's different. The way my hand is where she is, let's say, because Greta, that's her name. Greta is. And the way in which I am where she is, they're different. So clearly there is no just one notion of location, right? So for example, there's a sense in which I'm in this room. I'm located in this room, but it's not the same sense, right, in which I am located where my heart is. And there's a bunch of notions of location. And you might think, look, well, you have to distinguish those, because of course there are senses of I am where my parts are, where the upward inheritance of location just fades, right? Because of course I am not in the same way locationally related to this region as my hand is. Okay, so you might think, look, once I actually have clear distinctions about different notions of location, I'll write down precisely upward inheritance of location, you will see that the problem will go away. Unfortunately, that's not the case. Because this is the one that I can think of, which is not too soon. In the book, we have a distinction about, I think, 14 notions of location. So we're not, of course, we're not going to do this. Okay. So this is just, but this is a version of the principle which I tend to think is fairly natural. Okay. And it is violated in this case. It says that if x is part of y and y is exactly located at R, then x is weakly located at R. Now, as of now, I'll have a formal theory for you, but as of now, the principle mentions two notions, right? Exact location and weak location. So as of now, you can intuitively think the following way. These are taken from Parsons. Exact location of an object is always shadow and substantive in space. Space-time, take Brydon's now, is the region that has the same shape, size, stands in the exactly same locational relations, and so on and so forth. Okay, so if you take this, the exact location of this bottle is this bottle-shaped region here. It's not the bottle-shaped region here, it's the bottle-shaped region here. Weak location is just the locative notion that an object bears to every space-time region which is not completely free of it. Okay. It's the weakest possible, in fact, it's the weakest logically. Every location relation that entails it entails none. Okay. So the thought here is that, well, there is a sense in which I'm located in this, I'm weakly located in this room, because this room is not free of me. You can bump into me in this room. Okay. So for example, if I do this, which is the thing I do always when I teach, like if I do this, right, you can see I'm weakly located both in the corridor and in the room, right? Why? Because you can bump into me both in the corridor and the room. And I'm also weakly located where my hand is, because it's not free of me, right, that my hand is there. Now, if you do that, this seems to be a very, very natural principle. It literally says, well, if my hand is part of me, and I'm exactly here, then my hand is somehow here. Like it literally seems very, very weak. Very, very natural, very, very weak, and it still gets violated. Okay? Because of course the region is exactly located, the region, by region is somewhere is exactly located at itself basically, but the parts are not even weakly located. In fact, they're not occupied at all. They're not in that space. That's the thought. Okay? So now, so the first point being like, you cannot just get out of the principle just by distinguishing notions of location and hope for the best. And because once you've done the distinction, there is a principle that uses those distinctions that still seems to be violated and seems pretty weak. So the thought is that one has to go. Okay. So for a long time, the thought was, well, you cannot give up neither upward inheritance, no region is somewhere, so meteorological emergence of space-time needs to go. Now, but I forgot to mention, let me be upfront. I don't believe in any of this. Like, I don't believe in any meteorological claim I'm making, in fact. I mean, so it's just for the sake of discussion. I don't endorse that. But I think that the argument is a little bit too quick. So because, of course, we've seen, I mean, this literature don't talk, right? So we've seen that in literature and formal theories of location, it doesn't seem that somewhere gets unchallenged. You might think that, look, I can turn the argument on its head, okay? And maybe it's just regions are somewhere that needs to be rejected. In fact, there are formal theories of location that do just that, meaning I'm just going to provide one. I'm just going to actually write it down for you, okay? And you will see it. It's not a peculiarly, it's a reasonable theory. I don't think it's a reasonable theory for quantum systems, but for classical mechanics, I think it's a reasonable theory. For example, it's just a toy model to say this can be done. But this is too quick because that's why we started chatting with Sam. Sam thinks he has two arguments in favor of regions or somewhere. So who cares about, thought is that who cares about your formal theories? I have two arguments coming, he thinks, from physics. For regions or somewhere, so whenever you have a clash between your formal theory and the physics, well, it's your formal theory that needs to go, which I completely agree. So here's the argument. Once again, I don't want to read quotations, I'd rather chat with you. It's just to see that if you want to check that I didn't cheat, you can go and check. So the thought is that there are two different arguments, but they're related. The first one is, look, If regions of space-time are not located in space-time, then how come they have spatial-temporal properties? You need regions of space-time to be located in space-time for regions to be, I don't know, topologically open, topologically closed, at distance from each other, any spatial-temporal properties whatsoever. The second is, you need locations of regions in space-time to actually locate objects within space-time. So the thought here with Sydney is, well, suppose that Brian is here, let's say in London. If London is not located in space-time, then I don't get that Brian is located in space-time, which is something that everyone wants. That's the thought. So they're related, but they're different arguments. So I'm going to call them spatial-temporal properties argument. Locations of space-time regions is indeed needed for space-time regions to have spatial-temporal properties, and is needed. That's the key thing. Not saying you might not want it, but it's needed. And location of objects, location of space-time regions, is needed for objects to be located in space-time. So these are the two arguments in favor of regions of somewhere. So the thought is that now you need really to abandon mereological emergence of space-time, which once again, I have almost no sympathy for. So now what I'm going to do is that, well, I'm just going to, the proof, what's the English saying? The proof of the eating is in the pudding? No, something like this?
Yeah. Proof of the pudding is in the eating.
Yeah, something, okay, sorry, I just mixed. So you see, doing location doesn't. So I'm just going to do it. I'm just going to do a formal theory of location that does all of that for you. So the thought is that you might not like it, but that shows you that you don't need it, meaning you don't need somewhere. In fact, I'm not going to use anything about the locations of regions to do the thing. So now you just need to take, this is, so let me, after 40 I don't see anything. Okay, so there's going to be two primitive notions. There's going to be parthood, x is part of y, and then there's going to be a notion of exact location that you just saw. These are the only two primitives you need. Okay, then you define overlap as sharing of parts. This is just having an empty intersection, if you know set theory. Then you define the fusion of some things that satisfy the open formula phi, or if you have included, so you might do an included logic if you want, so that you can actually get a theory which is finitely axiomatizable. If you do this, you're going to have schema, so that's the only technical difference, right? So you will not get a finitely axiomatizable theory in your head. You will have a schema, and then you will have a theory for each phi you plug into the axioms of your background theory. But this just says that Z is the fusions of the phi if every phi is part of it, and every part of Z overlaps one of the phi. It just says, look, it just says that the fusion is basically set theoretical union. It's the counterpart of set theoretical union. Doesn't say anything more than this. It's just fancy talk. Now the other, so there's a bunch of axioms in the mereology, but it's classical extension of mereology. Think of it in terms of, just purely in terms of set theory. And then you say that the second, whenever you have a location relation, the second argument place is going to be a region of space-time. Oh yes, so you have another primitive, being a region of space-time, sorry. Or it's another primitive notion. In fact, because that's for technical reasons. Like, you can actually define this, but you can define this in a theory of location in which you have the regions are located somewhere. Given that I don't want that theory of location, I need to take it as a primitive, as a matter of fact. So the theory of location I'm going to develop is not strong enough to give me the definition of this notion. I have to take it as another primitive. And now you define, and now you have perfectly, so you can define weak location, entire location. Purposive we will never see. Weak location is just the one that I told you. It's meaning that you have an overlapping exact location. So why I was weakly located both in the room and in the corridor, because my exact location, right, overlapped, shared the part with both the room and the corridor. An entire location here is just basically the formal rigorous analog of a very intuitive notion, which is being contained. Like, I'm entirely in this room, which means, of course, by the definition says, well, because I have an exact location, which is here, which is part of the room. Okay, that's what it says. Now, this is a toy theory, because I don't think it works for quantum mechanics, in particular for quantum systems. But there are other theories that are more actually, it might work for quantum mechanics, in which the argument is just more difficult and more convoluted. So that's why I'm going to develop this for you. And now upward inheritance becomes this. You should be able to, it just becomes this. If X is part of Y, and Y is located exactly located at Z, then X is weakly located at Z. So now you have just a formal once you have that, you can define the spatio-temporal entity as something that has a weak location in space-time. So for example, Brian, the number 7 is not going to be, arguably, a spatio-temporal entity in this technical sense. It turns out that you can say weird things, right? If you think that regions themselves are not located in space-time, technically, regions of space-time are not spatio-temporal entities. But you have to keep in mind that this is a very technical notion of spatio-temporal entity. It's not your run-of-the-mill intuitive notion. Then, this is just to say that if you have a mereology which is strong enough, which is extensional, which you have in the background, because once again, remember, it's just the counterpart of the set theory, you can just define a general fusion operator, which if you don't know what it is, it's just a notion of fusion prefixed by the Russell operator, by the Russell definite description operator. It just tells you instead of a fusion, it tells you that's the fusion. That's what it does. You don't get it for free, okay? In set theory, you get it from the extensionality axiom that unions are unique. Here, you have to force it, okay, somehow. And then you just take space-time as just being the fusion of all the regions. In fact, to be honest, so if you want to be very, very nitpicking with me, you need another axiom, which is the axiom that tells you that regionhood is closed under fusion. Of course, it's not closed under parthood, right? Parts of regions might not be regions, because we're doing this because we think that these people think that regions of space-time have whatever strings or spin forms, whatever they are. I honestly don't know what they are. But of course, you need to say, if you want to say that space-time is a region, then you need to enforce that it's at least closed under fusion. Why? Because mereology will not do the trick for you. There's no way of actually forcing just in a pure mereological theory that the fusions of a phi is a phi. In fact, usually that's not the case, right? Fusions of cats is not a cat. I mean, or arguably it's not a cat. Fusion of electrons is not an electron, and fusions of atoms are clearly not atoms, right? So you will have to actually have an axiom that says either that space-time is a region, or if the x fuses and each x of the x's is a region, then the fusion is a region. The fusion will exist, but you have to actually have it that's a region. So I didn't put it there, I'm sorry. So, but you have to. Just, you see, if you want to actually have it again, put it against me, you know, how many axioms should I put in my theory of location, which is not parsimonious at all. Like I have to specify that. I don't have any other means. Okay, good. So now, what I'm gonna do, I'm gonna just take the lead from Achille, Vazzi, and saying, but basically saying what we started with, right? There seems to be two ways from here. So this is the basic theory. You can prove a bunch of theorems. In the theory already, at that very scan theory, you just can prove a bunch of theorems. And then you have other two different extensions of the theory, and the extensions are actually look at the locations of regions. And here is the quote by Achille. It says, look, if you think they're located, then the obvious thing to say is that such entities are located at themselves, regions of space-time, okay? So what we're going to do is that we're going to add this axiom. You're going to say that if X is a region, then it's located at itself. Now, if you have this theory of location, you can define this. As a matter of fact, it turns out that you can define the R predicate. So you don't need to actually have it as a primitive. But of course, I want to go the other way, so that's why I actually have it in the thing. And of course, now it's just going to turn out that regions are spatio-temporal. So regions are somewhere, it's going to be something like this. It's going to be, well, if it's a region, it has a weak location in space-time. It's weak location, it's somewhere in space-time. That's exactly what it says. And now, of course, it turns out that these just regions, it turns out that under this notion, regions are spatio-temporal entities. In fact, it turns out that these are simply equivalent ways. Okay. Somewhere just says that regions are spatio-temporal and vice versa. Now, one technical bit is that in this case, this is the strongest notion. This entails this, but this doesn't entail that. So you will see that in the other way, it's going to be the other way around. It's going to be, so for the other notion, it's going to be that nowhere is going to entail the counterpart of this, but this will not entail. So the logical relations are reversed, as a matter of fact. So here's one option. And here's the other, I like the way Achille actually put it. He says, regions do not have a location, they are locations. So they're not themselves located. So you can say if it's a region, it's not weakly located anywhere. In fact, you can actually say that. So that says regions are not exactly located anywhere. This says regions are not even weakly located anywhere. They're literally nowhere in space-time. Now for this thing, as I was saying, the logical relations go the other way around. This one entails this, but this one doesn't entail this, as a matter of fact. Okay. So this tells you that regions are not spatiotemporal. In this technical sense, they're space-time regions, but they're not spatiotemporal entities. Of course, in this very technical sense, right? And this is just, and these are equivalent, but you will have to keep in mind, if you want to do a little bit of, I don't know why you wanted to do it, but check on my formal work, but if you want to check, whatever, right? You will have to actually remember that you have to add this. This will be not enough this time. You have to add this, which is stronger, as a matter of fact. Because if you look at it, it turns out that these are pervasive location, weak location. These are the logical relations between locations of relations. So when they go upward along the line. So as you can see, exact location is the strongest one and weak location is the other. So then you see why this one entails this one, but not vice versa. For the four ones that we saw. I forgot to put it. Okay, good. So now, so once you have that, my claim is that I can prove that objects are somewhere. I can first write it down, and then I can prove it. So recall the location of objects. First, the objects argument. Somewhere is required for objects to be located in space-time. Now, what does it mean? Arguably, it might mean two things. The other one seems, pervasive location, I didn't tell you, is the relation of, basically, it's the formal rigorous counterpart of the notion of filling, completely filling. So for example, Eleonora fills the regions of her left hand, but she doesn't fill this room, right? So why am I saying this? Because now the only plausible candidates for region objects are located in space-time is going to be either weak location or entire location. The thought being that I'm big, but I'm not as big as to fill the entire space-time. Only God does that, and He doesn't exist properly, so, right? So you might have, and you don't need, in fact, as you know from this now, right? This one will entail this one, but this will not entail this one. Okay, just by looking at this diagram. And it turns out that no matter, so I could do the argument for only this, right? The thing is, it doesn't matter how you cash it out. This will be always, you can derive both as a theorem, as a matter of fact. How do you do it? So this is done in the theory of location I presented to you, which is a little bit of a toy theory of location. So they're way more sophisticated than this. But you can do it like this. So objects are spatio-temporal entities, they're weakly located somewhere, therefore they're exactly located somewhere. And now, just by definition, okay, of weak location, entire location in space-time, they're both weakly and entirely located in space-time. Therefore, no matter how objects are located in space-time is cashed out. Turns out that objects are indeed located in space-time. And here the trick is the definition of space-time and how the regions are located to space-time. They're not located via location in the definition of space-time, they're located via mereology. Space-time is just the fusion of them. Okay. So the thought, so now, to be fair, this argument, if you do it rigorously, passes from the fact that the objects are exactly located somewhere, which you will get by the definition. By the definition of weak location I gave you, you will see that everything that has a weak location has an exact location. As a matter of fact, this is sometimes called exactness, which is a theorem of that principle. It says, if there is a y such that x is weakly located at y, then there is a z such that x is exactly located at that z. So everything which is in space, every spatio-temporal entity will have an exact location. So you can prove it. Okay. Now you might think that this is too strong. and I would agree. In fact, in the book we go over many violations of this, some of which may actually involve quantum entities. But the thought is that you can actually do it the same, you can do it in a much weaker theory of location. All you need is the following theorems, that if either they're theorems or if they're not theorems because you pick, for example, entire location as a primitive. We have in the book theories of location with entire location as a primitive. It's because of the following very, very natural axiom, which says that both weak and entire location are monotonic. Which is to say the following thing. If I'm weakly located here, and this is part of London, then I'm also weakly located in London. And then I'm also weakly located in the UK, and in Europe, and on the Earth, and on the solar system, and so on and so forth. Same thing for entire location. I'm entirely here, I'm entirely in London, I'm entirely in Europe, I'm entirely in, what I would say, the EU, but it's not true anymore. So whatever, you get the feel, right? So that's monotonic, right? So if you take the basic relation to be, to relate you to a region, and then you take things that have that region as part, you're gonna bear the same location relation, which seems very uncontroversial. If you give me a notion of weak location or entire location that is containment, which is not monotonic, okay, then I don't know what you're talking about, it seems to me. In fact, on actually views in which you can reduce location to parthood, for example, if you're a supersubstantivalist, this just boils down to transitivity of parthood. It just boils down to that. Okay, so they're pretty natural, and you can do the same thing. Are you going?
No, not yet.
Okay, no, sorry, I wanted to say goodbye before you go. So the important thing is that the argument does not require somewhere. Location of the regions is not needed to account. All that is needed is that regions stand in a mereological relation, not in a location relation to space-time. Either, and monotonicity, if you don't get it for free from the axioms. So in this case, you'll get it for free. Monotonicity of entire location and weak location, you'll get it for free, and you will also get it for free. Dissectivity of pervasive location. So if, for example, Eleonora feels her left half, she feels also the regions of, she also feels the regions of her heart. Because it's not monotonic, of course, she pervasively feels a region there, but of course she doesn't pervasively feel everything that has that region as an extension, right? Not this one. So pervasive location is dissective, weak and entire, monotonic, but not dissective, of course. That's the thought. And here, if you're logically minded, how you can see it. So you have a basic theory, and then you have two conservative extensions of the basic theory, okay? And the basic theory is the one you saw, and the conservative extensions, you get it by adding this. And you, as I said, like you need to add this, the strongest one here. You cannot add the other one, honestly. That's just a wrinkle in the proof. And the thought, of course, the arguments from somewhere, right? If you look at it this way, the thought is that the argument that objects are located in space-time, here a way of seeing that, is a theorem of this conservative extension. But it cannot be a theorem of this conservative extension, right? Because the thought is that it's required. Right? But if you look at it, you will see that the proof is done here. It's done in the basic theory. Which means, given that these are conservative extensions, it's a theorem also of that one. It's a theorem of all three of them, in fact, just by being a theorem of the basic theory. And that's enough to tell you that you don't need somewhere to derive that. You just can do it there. And therefore also here. That's the thought. Because you can prove that they're conservative extensions. Okay. Good, I think.
Can you just say,
yeah.
Claudio, what is being extended? Is it the domain of these operators that X and Y are ranging over?
No, it's extended meaning like you add another axiom.
Oh,
it's just, just the axiomatic base of the theory. Yes, exactly. And it's a conservative because it proves all the same theorems.
Right.
That's it. That's the entire thing. No, that's strict for strict domains. Good. No, that's good because otherwise. So that's done. So the argument actually, in fact, generalizes. So I took mereology because in formal theories of location, that's what people do all the time. But of course, there are people that, for example, have primitive notion of being a subregion. There are some people that just doing set theory. Okay. It actually, for suitable relations of elementhood, let's say, if you do this, if you define an entire location as the following thing, it's exactly located somewhere, and Y is an element of Z, being in the subregion, a subset, or a part, okay? All you need to do is, once again, enforce that this notion, which is containment, basically, it's what we actually intuitively think about containment, is monotonic, and then you will have the same proof. It will not change anything. This also responds, I think, to the space-time property argument. You don't need that they're located via, so there have to be some relation between regions, and perhaps between regions and space-time if you want to do some topology, let's say. But you don't need location. You can just have whatever elemental, whatever compositional structure you want. Set theory, plural logic, mereology, or primitive subregionhood. I think everyone will do the job, as a matter of fact. Even plural logic will do the job for you. If you don't have fusions, but you just have pluralities. And pluralities, of course, doing the theoretical role of the fusions, which AKA the unions in set theory. Good. So now that seems to give you here, which I was very proud of finding. So you just need to say that regions are nowhere. Now, so I was proud because I found the passage from the bell tones that literally says nowhere, nowhere, nowhere all the time. And of course, given that we are in London, right? So this is something that he sent, that Hemingway sent. Someone that actually wanted the book, and of course, there's the famous Meditation 17 by John Donne, right? The one that no man is an island, right? That's where this comes from, which is here. I mean, it's here. No, St. Paul is far from here. No. It's right. Okay, so you can go and see his tomb, and you can say, last time I bought myself a $500 Bible, actually with comments from John Donne. So this is the famous, it has a fantastic metaphysics of death, right? Because it literally says that every man's death diminishes you. Why? Because you're just involved in mankind. And so the thought is that you shouldn't ask for whom the bell tolls, it tolls for thee, it tolls for you. And there's also a great Metallica song, so I mean, what's not to like? So, and this is actually the right, any man's death diminishes me because I'm involved in mankind. So it doesn't, but it's literally, it's just 2 lines before, it literally is the famous one that says no man is an island. It's like literally 2 lines before. So if it were for that, we could just stop here. We could have said, look, now we have a reason, also in the theory of location, to say that regions are not located anywhere. Okay. Now, I might have other reasons coming from measure theory, actually, to say that. But the thought is that at a certain point, chatting with Alice Sané, it turns out that she has a view which is relevantly similar to this, but different in 2 respects. First of all, it's a little bit different because the axioms that were going to be violated, they're very similar. So if you don't do formal theories of location, you will not almost see the difference, but they are different as a matter of fact. But more importantly for this, it cannot be actually undermined by with this. So I needed to redo it again. And so I'm starting to think about general ways. So once again, unfortunately, there seems to be another quantum argument that's relevantly similar, but different, importantly here, because it cannot be resisted by switching to nowhere. In fact, no one will do it. In fact, I was thinking about it this morning, but then me wanting to read in a pub got the best of me. So I didn't think too much about it. I tend to think that you cannot nowhere will clearly not do the job because it does anything to do with locations of regions. So nowhere, the literal sense of nowhere will not do anything for you. But you might think that the counterpart of nowhere for the entities that I'm going to talk about will do, and I tend to think now that it will not. So you literally need a radically different strategy. But once again, London got the best of me. I wanted to. So, and the thought is that here's the view that Elisa defended, and so the monistic part, David Albert didn't defend it, as a matter of fact. But Elisa defended all these views. And they're controversial to say the least, but we chatted for a long time about this. So the wave function field is the only fundamental object in quantum mechanics. But the wave function field is just a field defined and located, in fact, she says, over configuration space, or high-dimensional space. Three-dimensional objects exist, and that's the crucial claim that she wants to make now. She wants to make it in a paper and then in the book. So she wrote an entire book, beautiful book. And they are mereological parts of the wave function. That's because in the book she rehearsed many attempts by David Albert, by Peter Lewis, by Jill North, and she says, look, here's the best way, Alex is a part of the wave function field. He's literally a part. It's the same relation that his heart bears to him. And then she just wants to say that the wave function field is exclusively located in configuration space. 3D objects are exclusively located in space-time, and they're disjoint. They literally don't share any part. Okay. Why is that? Wait.
45 minutes.
So it's 45 now? Oh, fuck me. Okay, I'm gonna step up. And here she said, well, I'm gonna skip that. So I'm gonna skip that, because I think she came to understand that I was right at least once in my life. But this violates this axiom. It violates if X is part of Y and X is exactly located at region R, then Y is weakly located at R. Okay, why? Well, because let's say Brian suppose that he's exactly located there, okay, and is part of the wave function field. So this axiom will tell you that he's weakly located there, but it can't be, right? Because the wave function field is just in configuration space. But this seems pretty natural. It literally says, right? It literally says that if Brian is, which is which? Okay, so if Brian's hand, right? Brian's hand is there, where here. Brian's hand is here, so he's here too. It's just weakly there. You can find it here. Like it seems very natural. Now you might say, wait a minute. So here's how it's inconsistent. Suppose that the wave function has non-zero value at one point, then the particles will be exactly located at the end points. So the wave function field by the axiom will be weakly located there, which is inconsistent with this joint location. Now you might say, wait a minute, this is incredibly exceptional. Generally the wave function will be spread out in configuration space, and it's unclear that you should say that the particles, let's focus on particles, will have an exact location. It's unclear that you should say that. In that case, if you don't want to say that, then it would be vacuously true. The problem is that there is another principle which actually has weak location rather than exact location in the parts, which will be still violated. And that seems actually very natural as well. Okay, now what? What do I do? Okay. Note that the inheritance principles are similar yet different to the ones. So here's all of them. So as you can see here, you have exact and weak. So this is why this is weaker than this. And in the other ones, in the upward, you had that the whole was located rather than the part. And the consequent all enforces location of the other thing. So that's why they're not the same. In the quantum gravity case, it's the whole that it's located, here is the part. And then the consequent will enforce the location of the other guy. That's the thought. So they're literally different. Now, here's what Alyssa told me. So you just need, you metaphysician, still don't understand the following thing. Physics tells you the following thing, that you have to actually revisit your principle of location. You took it for granted, you like them because you just work and this toy picture of the universe and so on and so forth. Now, and physics actually tells you that you have to revise a lot of principles. And I completely agree that physics actually, usually, it's more, makes us consider possibilities that we're not even the wildest of imagination. I grant you that. But the thought is that it seems to me that this is a little bit too quick in this case because of the following thing. It's not just, it seems quantum physics. It seems quantum physics together with a very controversial metaphysical claim, which is the mereological claim. That the regions have parts that are not spatiotemporal. In that case, that Brian is a part of the wave function field. That thing, I don't think you get it just from the physics. It seems to me you might want it, but you have to defend it. Like this is not just something that comes from the physics, that the relation is mereological. And I want to show you that in the light of the above, one might prefer to give up such mereological claim. In fact, I would be tempted to do that. The arguments show that mereology is not the right relation. Now, and that pains me to say, because mereology is one of the two things I know. It would be great if it was mereology, because then I wouldn't have to study anything anymore. Right? I tend to think that that's the right reaction. But it's important that one understands that it is mereology that creates the problem. If you actually switch to another relation and you plug it into the locative principle, you will not get anything which is remotely actually natural or compelling. So here's one example, which is stupid because projection probably it's not a two-place relation, it's X, you project it. So the relation should be Y is a projection of X onto Z, but it's just so that I can just copy and paste a drawing to make you see that the principles will not have any plausibility in the case of projections. Okay. So my philosophical meaty notion to do that is counterpart. I tend to think that if you actually have the counterpart of the locative principle where you plug in counterparts rather than parthood, then you will have principles that fail all the time. In fact, here are the principles. I just rewrote it, just using projections. Okay? So these are the same principle. Instead of X is part of Y, you say that Y is a projection of X. But as you can see here, right, usually it's quite intuitive to say that projections and projected things have disjoint locations. So these principles will not have any plausibility. They literally depend on the fact that you have mereology at the first conjunct. Okay, so now what? Clearly nowhere in its original form is no use here, right? Because there's nothing about regions. I don't think it also the counterpart of nowhere for the wave function field will help, because I think the problematic claim is now at the consequent, it's not at the antecedent. So the thought is that it will not be vacuously true, because the consequent, you will get the antecedent, so the principle will tell you that the wave function field is located in three-dimensional space, which is one thing you want. So my guess is that really you need something else. And my thought was, yes, there is. So if you look at these principles, they always have the same form. You think that there are two things that are related mereologically, they don't occupy the same space, so to speak. Right? So one is in the kitchen, one is in the bedroom, and then of course you say they're mereologically related. Now of course the first temptation is to say, well, if you tell me there's a bowl of clay, a bunch of clay in the bedroom, and Brian is here, and I ask you, what's the relation between that clay and Brian? Chances are you will not say parthood. I grant you that. But suppose you want to stick to that. The thought all these examples work in that way. They just don't share the same locative space. So now the thought is, well, what if I take Alisa had her words and say, maybe what physics is telling us, if you want to do this, I tend to think that mereological claim has to go. But it's that, well, when we always thought about principles of location that actually were thought of for things that occupy the same space. What if we restrict to those? And now here's a couple of ways of doing it. So say that an occupant, for example, of space-time is a spatial-temporal entity. There's some part of space-time at which it's located, and you say that two things are spacemates if they're both occupants. So for example, Brian and I will be spacemates. This is a general notion because I tend to think the location is general. So for example, in the book, we defend this view. So for example, Brian and I are not just space-time mates, we're also world mates, meaning we occupy the same world. If you think that location is the relation, it's the right relation. So now you might do that. So you might actually stick an antecedent to impose a restriction on the principles. Say they are restricted to spacemates. So what I did here, and I'm very proud of this LaTeX thing that I did. So if you can see here, I just did that. These are just the same thing. I just put an antecedent that says, oh, by the way, they hold when the two things that mereologically related are spacemates. And now the thought is that they don't violate this. This will be trivially true, okay? Because this one will be violated. Of course, you can put it as a conjoint here. That's what I've done too. So someone made me think that depending on the mathematical structure that you have, well, it might work in this case, but in very general field of regions, it might not be working, because if you only set theoretic structure, then you just state the union, and they will be per force spacemates on the union. So you need another way of doing that technically. So the restriction strategy will fail, and I'm almost done. So here's another way of doing that. Just stick a conjunct that says, so the principles work like this. One, you know it's either the part of the whole, you know that it's an occupant of the relevant space. You don't know that the other is. Then just actually enforce that this principle work even when the other is. So here you will have to plug the whole, and here you will have to plug the other way around. You will have to plug the part, and you will have to plug the whole. And this will work also when the mathematical structure that you have behind is weak enough, like just purely set-theoretic structure or purely methodological structure. In the other case, it will be no guarantee that it does. Of course, for more complex mathematical structures, you might say, well, you know, it's not a given, right, that two metric spaces, the union is a metric space, because you don't know whether the union of the distance function in one is, and the other one is going to be a distance function on the entire thing, right? So it's not guaranteed. So for various, let's say, structured spaces, even the other restriction might work, but to be on the safe side. Now, I like this, and then you have to take another step, philosophical step. I tend to think that at least I should say that the plausibility of the inertian principle stand or fall with the restricted version. It's just that physics told us that we should actually look at things that are not space-mates. And then, if you do that, just know that the quantum cases do not provide violations, neither the quantum gravity case, nor the simple quantum mechanics case. Of course, I like this in general. I mean, once again, to put my card on the table, I tend to think that the right reaction is to abandon the methodological claim. I tend to think that Alex or Gingy or Eleonora are not parts of the wave function. They might be related to the wave function, but they're not parts for different reasons. But if you want to say, I like this strategy because it makes you say that location is way more general than location in space-time. And I tend to think that's correct, independently of philosophy of science. I tend to think that Wittgenstein is right when he says that a proposition is a location in logical space. I think that colors might be locations in color space, and so on and so forth. I tend to think that if you say that the king is in C3, you're making a precise locational claim, and so on and so forth. So I'm not thinking that's metaphorical. Of course, it's metaphorical when I say, like, you know, Eleonora is always on my mind, right? That's metaphorical location talk. Like, and in English, you have metaphorical location talk every time, right? Because even to express your feelings, you're in love. Like, it seems location talk, but these are metaphorical. But I tend to think that the king is in C3. It's just a real location talk, location claim. And in fact, what you have to do is that location is more general, and I wanted to finish with, this is Little Gidding. Because, you know, T.S. Eliot being London, in Little Gidding, actually, it's crucial that you recognize that there are other places in which you can be located. In fact, eternity, it actually resolves some of the contradictions that he's been exploring in the four quartets. In fact, you just have to see that this is nearest in space and time, but there are other locations. In fact, there are other places. And that's crucial for the fourth quartet. This is Little Gidding, and I thought that actually finishing with T.S. Eliot here might have been.